Microsoft Paint technology.
We'll just wait a few more minutes. We just finished our lab meeting and we're transferring floors to unlike the virtual office, you actually have to pick up and move things in the real world. Okay.
Can we start?
Yeah, I think so. Hey, Sophia, is everyone ready down there? All right, so let's get started. I'll introduce Stanislav for those joining in from remotely. Stanislav has been the kind of lead engineer, software engineer, and overall engineer. He fixes us all the hardware problems as well. So for many years, I think. How many years have you been with Backup Ray? Like 7 years?
7 years now.
Yeah, it's perfect. And so he's been nice enough to take some of his time out of his busy schedule to teach us newbies on how to program the Arduino. So Stanislav, take it away.
Okay, so I'm Stanislav Mircic. You can reach me at stanislav@backyardbrains if you need .com. So we will be talking today about Arduinos and how to use them, particularly how to use them for the purposes of this summer fellowship, and how to use it with Edge Impulse also. So we will try to collect some data, try to control some hardware. We will talk about common pitfalls that you will probably encounter during your work on your projects, and we will talk about limitation of microcontrollers, why microcontrollers cost $5 and computer costs 2,000. So let's start. So you are all familiar with the probably for sure you are familiar with the components in your computer. So you know that inside your computer you have processor, you have hard drive, you have RAM memory, you have some additional cards like audio card on which you can record the data and drive a speaker, and all of that costs about $2,000 for a good computer. And if you want to control something for a small amount of money, you will try to find a cheap computer, and basically cheap computer of today is a microcontroller. So in a microcontroller, you have all the same components. You have something that is doing the same job as a microprocessor. You have something that is doing the same job as a hard drive. You have a RAM memory. You can have a Bluetooth. You can have a USB, some timers, and you can have even something that's very similar to audio card on which you can record signal and play signal. So all of that is embedded in one single chip. That's a couple of bucks. That's the price of a cup of coffee. And you can access all of that through the external pins of the microcontroller. So only difference, one difference between a PC and a microcontroller is how we call different parts. So the microprocessor in a microcontroller is called arithmetic logic unit. Hard drive, where you put your program, is called the flash memory. And RAM memory is also called RAM. Sometimes it's called SRAM, but don't be confused. And something similar to sound card in microcontroller is ADC, or analog to digital converter. So that's one module in a microcontroller with which you can record some analog signal. Like in our case, we will record EMG, we will record EEG, we will record accelerometer data, etc. So you can also create the analog signal with a digital to analog converter, and that's very similar also like sound card. You can also, for example, record a sound of a microphone, very similar to sound card. All of that, it's embedded in one chip in a microcontroller. So in order to use microcontroller, because it's a single chip, it's very hard to do anything with it if you are not electrical engineer or professional. So people made a microcontroller board, and one of the famous companies that are making microcontroller boards is Arduino, of course. On that microcontroller board, they gave us easy access to all the pins of the microcontroller. They added a jack for USB, for example, so the connector for USB. They added power supply for microcontroller. They added additional sensors. They added reset button. So everything that we need to run the microcontroller. So this summer, we will be using microcontrollers, or precisely these microcontroller boards, for three things. We will collect the data with them. We will run neural networks or our models of microcontroller, and we will control some external hardware. So we are lucky then, in order to run neural network, Edge Impulse and a similar companies already created all the code that we need to run neural networks. So we will not spend too much time on programming this part of the code, but we will spend a lot of time on collecting data, and we will spend some time at the end on controlling the external devices. Like, for example, if someone has a project with a robot hand, then he or she will control the motors, and probably some students will control LEDs and similar. So let's start with actually some programming. So the first thing that we will do is to try to control some hardware with a microcontroller. So let's first start with one example, but before that, first we need to make sure that everybody have Arduino IDE. So do we have Arduino IDE installed on our computers, at least students? So E.T., I cannot hear you. I don't know what are you talking, but anyway, so everybody has a IDE. Next thing that you will need is to download the examples for this workshop. So I'll give you a link now for the examples. I'll paste it in the chat. Let me see. Okay, please download the zip file, or tell me that you cannot download it if there is a problem with the sharing. So I will need some kind of feedback when you download it. Just write something in the chat so that I know that you finished the download. Got it done. Okay. I guess you downloaded now the zip and that you have Arduino IDE. Next thing, you will have to make sure that you have a library that's used for accelerometer sensor. So if you go to Tools and then to Manage Libraries, there will be search box at the top at which you can type in this Arduino_LSM9DS1 name of the library and make sure that it's installed, that you have this green installed on the written. So please also give me some feedback in the chat if you cannot find the library or just say something. You don't have to write in the chat.
I just found it and installed it.
Okay, thank you. Okay, let's say that everybody installed it. And let's start. So the first thing that you will see when you open the Arduino IDE, does anybody have a problem installing the library? No, okay. No, okay. So the first thing that you will see when you open the Arduino IDE, it will give you a simple example, empty code, and that empty code will contain two functions. It will contain a setup function and a loop function. Probably majority of you know that, but let's just repeat the basics. So the setup function is the function that will run only once when you run the code. And in setup function, you usually want to initialize some things, so things that you want to run just once, and the loop function will constantly loop. So it will repeat the code that's between those two brackets of the loop function, and it will repeat it indefinitely. So it will start from the beginning and to end, and again from the top. So it can loop, depending on your code. If it is a short code, it can loop even a million times per second, or it can just execute one loop in a few seconds, depending on your code. So that's the basic structure of the code for Arduino. Every code for Arduino has that. Okay, let's first try some simple example. So let's try to blink a LED. So the first piece of the code that you have to run in order to run a LED is, if you open the zip file that I shared with you, workshop Arduino zip, inside that you will find Arduino examples directory, and then you will find a LED control code.
Should we open this example? Should we open this example from within the Arduino IDE, or is this something we open through File Explorer?
You can just double click on it, and it will open in the Arduino IDE. Or you can go to Arduino IDE and open the file. But you should open it inside the Arduino IDE. Yeah. Okay, I will stop sharing just to go through that with you, but I think you know how to do that. Your entire screen. I'll share the screen now.
I'm having a little trouble opening up the Arduino example.
Okay, what kind of trouble? So when you double click on it,
Sorry,
what
can't hear.
happens?
Oh, it's because through this. Sorry, so could you say that one more time?
So what kind of trouble? When you double click on the name of the file, what does it say?
It's asking what I want to use. Oh, I guess it's just asking what I want to use to open. I can't necessarily.
Yeah, assign the Arduino. Or you can open the Arduino ID, go to open, and then browse to the file.
Okay, I'll do that.
Maybe that's yeah. So let me do the same thing on my
No, but
side.
wait. So Stanislav, so I'm also having trouble. You mean to import it as a library or to open it? Just open it.
You just open the file.
Because they won't do that. It only opens INO files. At least in Windows.
So
It says Arduino.
can you see my screen?
Yeah.
So I went to File, Open, and then Workshop Arduino, then Arduino Examples, then LED Control, and then Open. And it should open the file.
But then you do want us to extract first.
Yeah.
Is that an extraction? Okay.
Yeah, extract the zip file first. Yeah, it's just zip file with a bunch of different things. It's not library for Arduino.
Yeah, I get confused with this adding libraries.
Come on. Yeah, added the zip. Yeah. No, it's much simpler. It's a simple Arduino things. Yeah.
All right, I got it.
So if you open the file, now you can connect. Do we all have Arduino BLA sense?
Yep.
Okay, so connect that to your USB.
I'm sorry, I didn't understand your question, Stanislav. Could you ask that one more time?
Yeah, do we all have Arduino BLE? Yeah, sense board. Yeah. Please connect that to the computer, so to the USB, so that we can upload the code. When you connected the Arduino to computer, do we all have the cables? Do we all have the board? If somebody doesn't have a board or cable, please write something in a message or just say something. Better say something. No, you don't have one? Okay. So I guess if you don't have one right now, you will have just to watch what we are doing. But I will try to explain the code. And okay, once you connected it, just hit this arrow and run the code. You should compile the sketch and upload the code. It takes some time to compile the code, even though it's very short. That's interesting. Yeah, before that, you want to make sure that your board and that you selected Arduino Nano 33 BLA for the board and that you selected correct port. If you have any problems, please write something in the chat or say something.
Can you hear me, Stanislav?
Yes.
Yeah. So I'm on a Windows computer, and I tried to upload the code, and I got an error that says serial port not selected. Is that that thing I need to connect?
Yeah, probably with the port. So go to tools and make sure that you selected the right port. The port is usually
Oh,
yeah.
port. Right there. Awesome. Thank you.
Thanks, Tim.
Sure.
So yeah. So if you click on this arrow button, it will upload the code. First it will compile and then it will upload and it will write something like done uploading at the end, depending on the UI that you have. Thank you, Computing Brains, for a proposal for simulated Arduino boards, but I don't know how that works, so I cannot help there.
Two of us are having an issue where it says an error occurred while uploading a sketch. I can drop a picture of that there in the chat if you want. Who? Me and Ari.
Okay, I didn't have Arduino Nano. So make sure it's the right Arduino on board.
Who's bored? Yeah, it's right about you don't know you're doing a nano. You have to change it to nano.
Yeah.
Yeah.
Arduino boards right there. Right,
Yeah.
nano.
Yeah, always select, for board, always select Arduino Nano 33 BLA. It's in the Arduino Embed OS Nano board. And for port, always choose port that has Arduino Nano BLA.
Nano BLE, do we have to choose another nano board or just Arduino Nano is fine?
Arduino Nano BLE.
Ooh.
I think you have to
go to the
You have to download the driver for that.
Yeah, you have to download the driver.
The board manager.
That was really
What's
I'm not gonna release that now. No, this was from the course. Sorry.
Usually when you connect the board, if you don't have the driver, the Arduino will offer you to the driver, so in the bottom left corner. So
Just you I just did. Yeah, just installing a driver for it.
But is that the right one or does it need to be the Nano BLE?
Oh, okay. No, this is installed.
I canceled with others around.
yeah, my driver for that board is Arduino Embed OS Nano board.
Here's the install deprecated.
Okay, we will wait at least this time for this first example so that everybody upload the code.
Oh, sweet.
Can you please just write down in the chat if you managed to upload the code and that you see blinking a red light? So just write anything in the chat so that I know how many people. I see blinking down, got it, the red light blink. Okay.
Yeah, why does it take so long to compile and upload to an Arduino?
Yeah, I think that upload is pretty fast, but I mean standard. But compilation is a bit long, and that really depends on the library, how they wrote the library. My guess is that it's because it's pretty universal library, it has to go through a lot of things to checks and you know.
Yes.
Right.
Yes. Alright. Now I'll go back to the Arduino. We are in it, but then I'll go to tools. You have to find it. You usually don't have to do this. Arduino embed OS nano boards. There it is. And let's see if it'll compile.
Samuel and Tim, so did you find a...
Yeah, you get an old way it's compiling, but I think
Okay.
we've solved it.
Okay, cool. Let's wait for everybody to, so then it will be easier later.
When you done.
Yeah.
Oh, you can copy it.
Mm-hmm.
We're just waiting.
You have to update this, right?
You have to uninstall it.
Oh, okay.
No, you did the wrong one. Which one? This one you want, this one you don't want.
Okay.
Done uploading.
Alright, we got it. We did it. We're good.
Great.
Art is still doing it, but we know the correct process.
Yeah, I'm just gonna
you go first.
stop
Yeah,
this.
sure.
Yeah, y'all can go on if you want.
Okay, let me share
You know,
again. I don't know if I'm sharing or not or what's happening here, but I will figure it out. Okay, can you see my presentation? Yeah, okay. Okay. So, so let's see what's in this code for a blinking LED. So if you uploaded the code, you will see a red light blinking every second. And let's see how we did it. So first, every microcontroller has a bunch of pins. And those pins don't have just one function, but can have multiple functions. So you can use it to communicate with USB or some external device. You can use it to power a LED or to get some input from outside to record something, etc. So the first thing that you need to say to microcontroller is, if you want to use some pin, what will be the function of the pin? So in the setup function, you can see that we said something like pin mode red and then output. So the red is a constant that actually says which pin we want to configure. In this case, it's a pin 22. Later, I will show you the diagram on which you can see which pin is which number. And we said that it's an output. That means that it's a digital output, which means it can output true or false in a logical way, or it can output actually 3.3 volts or 0 volts. So these are all different states that it can have. So first we have to always set up, if we want to use the pin, we want to set up the function of the pin. We want to tell to microcontroller. Then when when it finishes setup, it jumps to loop. And then we first turn on the LED. With the digital write, we write 3.3 volts on the pin, and that will light up the LED. Actually, this LED is configured on the board in a way that when you put 0 volts on the output, it will light up, and when you put 3.3 volts, it will shut down. Don't get confused with that, but it's just like that. Between those two digital writes, we have this function delay, which will just block the execution completely of this code for 1,000 milliseconds. This parameter 1,000 means 1,000 milliseconds, which means yet 1 second. So this function delay is useful for beginner demonstration or something like that, but it's not very useful because it blocks the code for 1,000. So microcontroller is not doing anything for 1,000 milliseconds, 1 second. So the specific thing about microcontroller in comparison with the processors is that microcontrollers do not have multiple cores. So it cannot do anything in parallel. It will do only just one thing at a time. So if you say delay 1,000, block microcontroller for 1,000, it will just be blocked and it will do nothing. So, okay, so this is the first example. This is the example of controlling something. Because I'm not in the office, I cannot connect the things on the board. But you saw how it controlled something that's outside of the microcontroller. Microcontroller is just this metal can at the bottom. It controls the LED. You can see the red arrow LED is outside of microcontroller. The same way you can control anything that you connect on the output pin, on the pins on the sides of the microcontroller board. You can control LED as Chris did yesterday, or you can control motor or whatever. So, and the code will be exactly the same. Just you set a pin mode for a for a pin on the board, and you will say digital write. Okay.
Can I ask you a question?
Yes, please. If you have any questions, just jump in. Okay.
So at the very top where you say define red 22, obviously you're setting that that pin, the 22 pin, to be that constant red. I was writing this code. I would have expected that to be inside the setup function. Is it important that that constantly be defined outside the setup function, or is that somewhat arbitrary?
No, you can actually say pin mode 22, and it will work. So you don't have to define it as separate, but this is just mnemonic way to do it, because we have to repeat it, and then if you want to change it, usually you want to set this define, because if you want to change the pin, then you have to go through the whole code and change every place where you put the 22. In this case, you can just change one place, and it will change the whole code. So that's why we use these defines. So they are not important. You don't have to use it. So okay, so this is the first example. That was example of how to control something with a microcontroller, and now let's make an example. Let's see example of how to collect data, because that will be the maybe even majority of the work that you will do during this summer. How to collect data. So let's first talk about this analog to digital converter. So analog to digital converter is something, as I said, something similar to audio card in a computer. So it can record analog signal, and it can generate, actually, if you want to generate analog signal, you have to use digital to analog converter, but they're similar and similar functionality. So for example, you can connect them, you can take a microphone, common microphone, and just power it up and connect to one of the pins of the microcontroller. With a bit code in a setup function, you can configure microcontroller to read the voltage from that pin, and you can record the microphone signal into your microcontroller. You can convert it to a digital signal. You can also, and you will be doing that, you can take the signal, EMG signal from the speaker box, or EEG signal from the speaker box, connect that signal with the wire to the pin of your microcontroller, and you can convert that signal to the digital form, to the numbers, array of numbers that you will be using later. So ADCs, or analog to digital converters, usually have multiple channels, so you can record things in parallel, and we will be using them extensively. So how they work, basically they in this setup with a speaker box that you will probably use, you have, for example, in the case of EMG, you have small voltage on your hand, then the speaker box is amplifying that voltage, then that voltage is we take from speaker box, connect to microcontroller, and then ADC is converting that voltage to a numbers that it stores into a RAM memory. And then later we can access those numbers from RAM memory and use them for our experiment. So on this microcontroller board, there are several pins, actually 8 pins, that you can use to record analog signal. So you can see here that they are named from A0 to A7. And you can see there the red arrow is pointing at A0 that we will be using today. You can, if you want to use them, you can just solder the wire or connector on that pin and just connect with the speaker box, and it should be able to record the data. Of course, when you are recording something with ADC, you always have to have a reference point. So the measurement of ADC is always in relation to reference points. So that's why you need also to, beside this one wire that you want to connect to A0, you will need also to connect the ground wire in your experiment that will give a reference point for the ADC to measure the signal. So, but let's start with this ADC example. So if you open yeah, please.
Can I ask a question?
Yes,
so,
of course.
Is there some sort of protection against providing too much voltage on this? Or if I'm recording signal and there's noise, it could be a huge.
Yeah, it can be.
output.
So, of course, that's something that we have to say. So, every microcontroller has a range of voltage that it can record. So, usually, that for these microcontroller boards, the range of voltage is usually equal to the power supply of the board. In this case, this is 3.3 volts. So power supply of this board in this configuration is 3.3 volts, and it can record the voltage up to 3.3 volts. If you increase a bit above that, nothing will happen, but if you increase few volts above that, you can fry the microcontroller. So it will just die. So in all our experiments, we will always first check what's the output voltage of the spiker box, compare it to the input range of the ADC on the microcontroller, and check if they match. If they match, then we can feed the signal into the microcontroller. Yeah.
So the spiker box
for that.
So the spiker box probably clips the output also at a reasonable level.
Yes. So the spiker box clips the maximum voltage that you can get from spiker box is 5 volts.
Okay.
So some microcontrollers can record 5 volts. Arduino Uno, most common microcontrollers can record 5 volts. This particular cannot, but we can always make simple voltage divider to lower the voltage. That's just, we will use 2 resistors for a voltage divider, and that will convert 5 volts to 3.3 volts and all other voltages accordingly. So there is a pretty easy solution. So spiker box will never output more than 5 volts. So okay. So because I didn't want to complicate it, and we will lose like half an hour if you want to connect now spiker box. I don't know if all of you have a spiker box at all. So we will try to read the voltage on this pin without connecting anything for now, but you will see there will be some signal on that pin, even though we didn't connect anything. So let's start by loading again a new example, read analog value.ino into a Arduino IDE. So I don't know if I will give you some time to do that.
Can you say that one more time? I'm a little.
Yeah, can you please load the read analog value.ino into the Arduino IDE? So it is file in the same directory, basically, or adjacent directory to the previous example. I'll do that. I'll stop presenting and do that. Share the screen. I will do the same thing so you can see how it works on my side. Okay. So file open. No. Arduino examples, read analog value, open. So it's a very simple code, and if you run it, it will compile and upload the sketch. So in this code, we are reading analog value from this pin. So we are using ADC. And then we are printing that value to the serial monitor. So in order to access serial monitor, you can go to Arduino menu, Tools, Serial Monitor.
I'm sorry, can I have 1 second? Oh, sorry.
When
When sorry, I'll use your.
when I went to recompile this code, it said that it wasn't connected to the device, so I think it'll be fine, but I just need an extra.
Yeah, please try to maybe to unplug and plug in again the device, go to port, select the right port, go to board, please check if you have selected the Arduino.
I find I have to go to port all the time because it disconnects and jumps to another port.
Yeah, so it will when you press the reset or if you if you unplug and plug in, when you unplug it will lose the power and then it will reset basically.
Yeah.
When it resets, it goes to bootloader mode that will actually change the port, and then you have to wait some time to change back again the port. So best to keep the board just connected like this and not to unplug at all. So.
I got mine to work, so if you want to move forward, you can.
Cool. So if you open the serial monitor, so again, you go to Tools, Serial Monitor.
Yeah.
You will see, or you can see at my screen, I'm sharing screen, you can see some numbers outputting. So these numbers are actually converted voltages to numbers, to digital numbers that are in your Arduino. So if you touch the pin A0 pin on the microcontroller, that's the. Let me see if I can show you on the screen. If this is USB, the pin is on this side.
Oh yeah, my serial plotter is fine.
I think everyone here has a blank screen for their serial plotter. Mine is blank, and so is Sarah's.
A blank screen? Okay. So when you open the serial monitor, one thing that you want to check is at the bottom right-hand side, there is a drop-down menu in which you can select baud rate. So you want to make sure that baud rate is 115,200. So again, if you take a look at the screen, you will see, so we are actually recording the signal from pin A0, which is pin close to the USB port. Close to the USB port, and if you can see me on the screen, that's the pin very close to USB port here. And if you open the serial monitor, when you touch that pin, you will see the numbers are changing. But that's not very interesting. You can just see what are the numbers. But if we go to Tools, and then first close serial monitor, but then go to Tools and choose serial plotter, then you can see the actual graph of the signal. Okay. And probably you will see something that looks like a sinusoidal or sinus signal. Okay, some waves. And basically you are looking at your future problem. So this is a noise that we all have in our body. So that's a noise that's coming from the mains. So 60 hertz mains noise, and it's basically present in all electrophysiological recordings, and usually that makes a problem during recording. So if you take a look at the screen that I'm sharing, you can see my signal, and you can see the same thing. You should see the same thing if you touch the pin on your side.
This noise when you do electrophysiology experiments is like the one thing that can make you truly superstitious. Because if you're planning an important experiment, you have these little things that you think might help reduce the noise, and you'll do all of them. And some of them really don't make sense. It's like, oh, I have to have the book. This book has to be here.
So you can see that you actually have a signal on your body, on your finger. You have some voltage that is constantly changing. Okay, and this ADC is recording that, sending through the USB cable to the computer. The computer is presenting that. Okay, if everybody managed to do that, then I can start presenting again. Present now, tab. Share. Okay, so how this works? Basically, again, this code for reading ADC, again, we have two functions, setup and a loop. In the setup function, we said that we are doing initialization. We are opening serial port. Basically, that's the way how to communicate through the USB cable with the computer. So serial port is one protocol that goes through the USB port, and it sends data to the computer. So how it actually works, it's a bit complicated, but basically you're just sending some data, it goes through the USB communication and pops up at the computer. So the one parameter that you have to set up when you are initializing the serial port is the speed of the serial port. That speed is here 115,200 beats per second. So it sends that many beats per second to the computer. Okay, that's not bytes. Bytes you have to divide it around with a 10 in order to get bytes, but because of some details about serial port, but that's how many bits is sent to the computer. Okay,
not with 8?
No, with 8, because you have start bit, stop bit in the serial communication. So that will take some of the bandwidth. Yeah, right. So usually people are dividing by 10.
Right. One other question. When you print to serial, it goes into some sort of buffer, right? So even if you print many things, the receiving computer, when it starts to read, it can get several messages.
Yeah. So how it actually works? So you print something. You call this function print. Okay. That function stores some value that you want to print or send to a computer, stores to some local memory on a microcontroller. Because microcontroller is waiting for a computer to say to him, okay, you are now allowed to talk over USB. Then it's waiting for a computer to say that, and when it says that, then microcontroller starts shifting out that data to the USB. Then it comes to a computer. Then on the computer you have computer USB driver that gets that data and then stores in some memory. And then your software like Arduino or Spike Recorder or whatever is periodically asking driver, give me new data from the USB or from the serial, and then it will receive the data. So it's a bit, there are a lot of things in the chain, but that's basically it. I don't know. So I hope.
But it's a short buffer kind of. So if you if your Arduino is sitting there recording and sending it.
Usually on microcontroller there is a half a kilobyte buffer.
Right.
yeah, just 500 bytes or something. So you can overflow it. If you write to serial print too fast, and computer is not asking you for the data, then you can overflow the buffer and you can lose some data that you write to serial print. But the serial print is pretty good function, and it's chances that you won't do that if you are using it in a common way. So yeah, because you need some time to get the data from somewhere and to write it down, etc. So I will later make a back on the envelope calculation how much data you can send through the serial port. So, but let's continue with this. So in this loop, you can see that we used analog read function. We said which pin we.
I think one person in the chat is having issues connecting their board. So what would they have to? I think I'm not sure. I don't know their screen, but apparently they can't connect to the Arduino 33 BLE Sense port or board. Sorry. So if you don't have that option, what would they have to do again? Do they have to just download the board?
Okay. So did that person manage to connect before?
No, I don't think so. No.
I think this is her first time trying.
So even the first example with the LED didn't work.
She said she's fine.
No. Let's try to help. So, or Chris, can you help? Maybe.
Yeah.
Is the person
Downstairs?
I don't know. Is person in the room or
I don't know.
online?
But you had the option in the drop down, didn't you?
No, they didn't.
Are you guys, if you're talking about me, I'm troubleshooting a solution that somebody dropped in the chat, don't worry.
All right, cool.
Okay. Sorry, then we will connect. We will continue. Okay, so the main function here with which we are reading ADC is this analog read. In this function, only parameter is the actual pin number on which we want to read, and or pin name from which we want to read analog signal. And in this case, it's a A0, and you can see from the pin out, you can read the name of the.
You're breaking up some. Myself.
I'm breaking up. Can you hear me?
Yeah.
Can you hear me now?
Or maybe it's just me. Maybe it was just me.
Yes.
Yeah.
Okay. Okay. So usually, if you just type in name of the board and a pin out, you will get image like this, from which you can see the name of each pin, and then usually analog pins are named like A0 to AN. In this case, A7, and you can just use that name to specify from which pin you want to read the voltage. Then you store the voltage in some value and some variable, and then you can later use it. In this case, we just print it on a serial port. Okay, so if we manage to do that, then we can go to another example. So right now we collect the data from ADC, from some pin. We can also collect data or record data from the sensor on the board. Basically, that sensor is also connected through some pin of the microcontroller to the microcontroller, just some other pin that's connected through the board. On this board, we have accelerometer sensor that has accelerometer and a gyroscope. So accelerometer is measuring acceleration, gyroscope is measuring angular speed, and there are only functions. The minimal number of functions that you need to know are these two functions. One function is to initialize accelerometer function begin, And other function is read acceleration, which will read three values, which will represent three values of acceleration of three axes of accelerometer. So if we now go further, and if you now open the third example in the zip file, the name of the example is read accelerometer. Oh, let me do the same thing. Let me stop sharing and do the same thing so I can show you. Yeah, first close everything and then open the third example. Read accelerometer. And then when you load the file, just run or upload the sketch. It will again first compile, it will take some time. So at this point, you may have a problem with the library if you didn't install the Arduino LSM9DS1 library, then you will not be able to use accelerometer. So, but I hope that everybody installed that library. So,
Stanislav, do you mean to share your screen?
yeah, I did it. Yeah, sorry. Okay, thank you. So I open the code.
Oh, cool.
Run it, and it just, after that you can open the serial plotter and you can see the accelerometer data. So
yeah, wow.
When you move it slowly, it will just show the accelerometer data, but if you move it fast or if you accelerate too much, it will light up the LED, red LED on the screen, on the board. Okay. And it will stop recording data.
And why is that?
This is because that's a common pitfall. Okay, I want to demonstrate something. So, can you see a code on my screen, or should I present? Because I have zoomed up version when I present, so maybe if you can see the code when I'm sharing screen, then it's...
Yeah, we can see.
Okay, cool. So let's go through this code quickly. So again, we have setup function. We are initializing accelerometer, but before that, we are initializing, like before, we are initializing serial port. We are initializing pin through which we want to control the red LED. We don't have to control red LED, but I added this part just to show you something. So in the main loop, we are just reading acceleration. After this function, we have acceleration values in the X, Y, and Z variables. We are printing that on a serial port with a comma in between, and basically that's it regarding acceleration. But below that, you can see that I took acceleration value of the Y component of the Y axis, and I checked if it is greater than 3G. And if it is greater than 3G, then I'm doing something. I'm lighting up LED. I'm lighting up LED, and because I want that LED to be easily seen. I'm just stopped for 1,000 milliseconds so that that user can see the LED. Okay. So what's the problem of this code? The problem of this code is that I'm constantly reading accelerometer, but if this condition is true, then whole code will stop for 1,000 milliseconds. So this is something that I see over and over again in code, that people are blocking their data collection with some non-related code. For example, if they want to turn on or turn off something, or even send data, or send serial print or something like that, everything will spend some time, and it will block the collection of the data. So that's a very common mistake. And let me just present. I don't know how to do this, but tab. Okay. So that's a very common mistake. And usually, for example, if you record EKG, and if you have code something like this that will do something else, for example, in this case, light up LED, in the same loop where you collect your data, then basically you will lose part of your data, and you will get data that's completely different than the original or real life data, and that can make all kinds of problems when you train your neural network on that kind of data. It can learn wrong thing. If you want to classify something, for example, if you are classifying, in this case, heart arrhythmia, you will get arrhythmia even though you don't have it in real life. So you have to pay attention on the loop where you collect the data, to make sure that nothing is blocking that loop. So that's a very common mistake. Okay. So the next thing that I want to talk about is the frequency of measurement of data. So, for example, on this slide, I plotted some data from the accelerometer, and you can see that this person is pretty fastly moving their hand. So it moves it makes 4 waves in 1 second. You can see at the bottom it's scale is in the seconds, and on the y-axis you can see acceleration is in G's. And the frequency of this signal, the main component of this signal, is 4 Hertz. The question is, how many measurements per second I need to make in order to get a real representation of this analog signal into digital form? So if we measure this signal, that's 4 Hertz wave, if we measure it 10 times per second, you can see here on the graph that you have red dots where we measure the signal. In the digital form, you will get something like this. Okay, so you still have 4 peaks, 4 kind of waves, but it's not really the actual data that we started from. So that's 10 Hertz for a signal of 4 Hertz. So more than a double of the frequency of the signal. So if we measure at 20 Hertz, so 5 times the frequency of signal, we will get something that's more closely resembles the original signal. If we measure it 10 times the frequency of the signal, we get something that pretty much looks like a signal. So imagine, of course, then when you speed up the sampling rate, then the signal will look better and better. If we measure it just the twice as fast as the frequency of the signal. Frequency of the signal was 4 hertz. Now we sample with the 8 hertz. We will still have the same number of waves as original signal, but it will not really look as the original signal. But if we go below twice the frequency of the signal, you will get false signals. You will get something that doesn't look at all like original signal. You will get something that has actually lower frequency than original signal, and that's just false signal that you collected. Okay, and because of that, there is some rule or some theorem that's called Nyquist-Shannon sampling theorem that says that you have to sample your signal or measure your signal at least twice as fast as your highest frequency in your signal. So if you're, for example, recording EEG, and your EEG goes from 0.1 hertz to 50 hertz, you filter it in that way so that your maximal frequency is 50 hertz. Then you should not sample it slower than 100 hertz, the double of the highest frequency. 50 hertz multiplied by 2 is 100. So, but usually, as you saw from the previous slides, even if you sample it with 10 times the sampling frequency, you still have some distortion. With the 5 times, you have something that looks like original signal, but it's not really original signal, etc. So you have to make sure that you sample you sample your signal, you measure your signal at a sample rate that's greater than 2, and usually you want more than that. You want 5 times the highest frequency in your signal. Okay, so these are the electrophysiological signals that some of which we will use this summer, and you can see the range of the frequencies for each signal. So you can look and find your signal that you will be recording. For EEG, here says that it goes up to 100 hertz. Of course, this is all open to discussion, but these are rough figures that are pretty much okay. ECG, again, up to a few hundred hertz, but you can useful part of the signal is 150 hertz, up to 150 hertz. EMG goes to a few thousand hertz, useful part of the signal. Of course, you can use just filtered EMG with a lower cutoff frequency, let's say to 1500 hertz or something like that. And make sure when you start recording your signal, make sure that your sampling frequency or your measurement frequency is much higher than a highest frequency in your signal. Okay, is there any questions about this?
Yeah, just to go back to the code, that sampling frequency was what we said when we did serial.begin, correct?
No. So let's not confuse. So serial begin is not sampling frequency. That's just communication, the speed of communication with the computer. So you don't have, in order to sample data, you don't have to have serial at all. So they're just for our convenience to present to a computer. So what's the frequency of sampling here in this loop? So basically, it's as fast as this microcontroller can go. Because, of course, if it hits the 3G, then it will stop for 1,000 milliseconds. But if it doesn't hit that, it will just loop around and collect as fast as possible these accelerometer data. So actual accelerometer has a sampling frequency fixed, but let's not go into details. But the code that you will be using will be something like this. So you will probably connect the spiker box to one of the pins and then use analog read to read the value. So analog read is pretty fast, let's say 5 to 10 microseconds. So it can read the analog value very fast, and depending on what you have in this loop, that will determine your frequency. There is another way to determine the frequency of the sampling, and that's by using timers. So one of the components, modules inside your microcontroller that's very important for real-time data processing are the timers. Those are small modules which you can configure to call one of your functions. You can create another function here called timer interrupt or something like that, new function. You create a new function. And then that timer module will, when you configure it, it will call your timer interrupt function periodically, and it will have a priority over the main loop, over setup, over everything. But usually it will execute after setup, so setup is not important. And with the timer function, timer interrupt function, you can guarantee the sampling frequency. So I didn't want to go into the details about timer functions because they are implemented differently on every microcontroller. But I just want to tell you that they exist. So there is a way with the timers to guarantee sampling frequency of your measurement. So we can discuss for each microcontroller, depending on the board that you are using, how to initialize those timer functions. But yeah, that's the solution basically if you want to have precise measurement. Please.
There was also a comment in the chat from Adam Steiner mentioning that there's some ability to maybe interpolate additional points. So, like, I don't know if you want to comment on that.
With post-processing, sometimes you can type additional values that something that could be built in the position stage, so you could sample a floor rate to run that yeah, so yeah, you can let me show this. Let me go back to this thing. So of course, if your measurement is slow and you are not satisfied with your results, can you see my slides? Yeah. Okay. If you are not satisfied with the shape of your signal, you can interpolate the signal, but that's basically you're making up the data. That's not something that we will usually do, but you can do that. The main problem with this is when your sampling rate is slower than highest frequency in your signal. Then you'll get some effect that's called mirroring, and it will mirror your spectrum. Anyway, you will get fake data like this one. You will get something that's 1.5 hertz frequency, and that signal does not exist at all. If you look at this red line, so it looks like some wave of 1.5 hertz frequency, and that signal does not exist in a real life. So that's the problem. So you can do whatever you want later with your signal, but please make sure to sample it at least twice the highest frequency in your signal. If you cannot do that, then please filter the signal so that you still satisfy that. So you take a filter and you just cut everything below the half of your sample rate, and just to make sure that you satisfy this Nick-Wishon theorem or the rule. Okay, I hope I helped. Yeah, it's called aliasing. Yeah, aliasing. Yeah. Let me see the question. Okay. Okay, let's continue with this. So make sure to think about this. What's the frequency of your signal? What's the sample rate that you will be using in your microcontroller? Okay, let's talk now about limitation of the microcontrollers. Particularly limitations for our purposes for machine learning. So if you take a look, and you can see the screen, yeah, you can see. Okay, if you take a look at the specification of the Arduino Nano BLE Sense microcontroller, so it's first of all, it's a 32 bits microcontroller, which means that the size of the number with which it operates, with which it arithmetic logic unit can add, subtract, multiply, etc. It's 32 bit. Okay, after that, the clock speed is 64 megahertz, which is much slower than your computer. So your computer usually has a few gigahertz, and it has multiple cores, which means like multiple microcontrollers, and at few gigahertz. And if you compare with this 64 megahertz, this looks pretty tiny, but it's actually not that tiny. If you think about it, it's 64 million operations in seconds. Because these microcontrollers usually calculate, for example, add or multiply in a single clock cycle, which means that it can do 64 million additions or multiplications in a second, which is pretty good actually, if you optimize your code. Flash memory or program memory, your program needs to fit into 1 megabyte of the hard drive of the microcontroller or a flash memory. And maybe most critical resource is this RAM memory, 256 kilobytes of memory. So how much is that 256 kilobytes? Okay, let's do some back of the envelope calculation with the data that we used already. So if we have a 3-axis accelerometer and its sample is at 120 hertz, which means 120 measurements per second, and if you recall, we store the measurements in a float data type, which is a floating point data type. It can represent not just whole numbers but also fractions. So that data type on a microcontroller takes 4 bytes. So for one measurement of one axis, we need 4 bytes. We have 3 axes and we have 120 measurements per second. If you take a whole RAM and number of bytes in RAM and divide by 4 bytes by 3 axes by 120 samples, you get that it can store 177 seconds of accelerometer data in that RAM, which is pretty good. So for this kind of data, we call it one-dimensional data series, when we are not talking about pictures or images, movies. This is pretty much a good amount of memory. Of course, EMG is much larger, you need greater frequency of sampling than 120. But usually it's enough for these time series, one-dimensional time series to store. Okay, so let's talk about images now. So if we take a small image, 200 by 200, or this small bunny, fuzzy bunny, and if you want to store it in a microcontroller, the question is how many of these images you can store in a microcontroller. So this image is 200 by 200 pixels. It has RGB values, so red, green, and blue, and each value needs 1 byte. You need 1 byte for red, 1 for green, 1 for blue. So you need 3 bytes per pixel. You have 200 by 200, and it comes up as 120 kilobytes of memory for this small image, 200 by 200. And it can actually store 2 images in the memory. If you want to use HD image, then you can just store 10% of one HD image in the memory of this microcontroller. So this is pretty much limitation factor for the video, for the cameras, for everything like that. So there are other microcontrollers that have microcontroller boards that have more memory. And if you want to process video or classify images, then you will probably use a different microcontroller boards.
And Stanislav, one question.
Yes.
So, because it takes so long to compile and upload these AI systems, do you have any sense for how much of this memory they eat up just living on the controller? Like a tiny ML project that like needs to be able to run TensorFlow Lite. Is it going to eat up like half the memory or almost all the memory? Or
how much memory? Yeah, I didn't look into the memory, but the regarding speed, we saw that the pre-processing in your case, for example, your example yesterday, pre-processing took 16 milliseconds
16.
for just 16.
Oh, 16, okay.
Yeah, for one frame, for example. And actual simulation of you had like 40 neurons, 40 something neurons. It took like 1 millisecond. So the actual pre-processing was much slower than actual. But when we come to convolutional neural network, then we don't have pre-processing, but then we have heavy neural network models. Usually you use convolutional neural network that you feed it with the raw data, and then you have convolutional. It doesn't have to be, but you have convolutional neurons. You will use them basically as a feature extractor. So instead of pre-processing, but then you have a bunch of computation with those input convolutional neurons. So they have to scroll over the whole data, and that processing takes some time. Etc. So I didn't. That really depends on how they program the code for this. I know that when you are, they made some optimization regarding how much space the code will take, because I know that at least when you write it in a Python, you have to specify which functions of a TensorFlow you will use in advance in the code, so that the compiler knows not to include all other functions in the program memory. So they have some optimization. It really depends on what you use, etc., etc. So they don't load whole TensorFlow library in the programming memory. They are just selecting. Compiler is smart enough to select just the functions that you use. Yeah. So hope this helps. Yeah. So if anybody else has any question, please.
Yeah. So Chris asked about compiling these models and then deploying them onto the Arduino. You mentioned that there was flash memory and RAM memory. Would those compiled models go into flash memory?
So when you compile the code and the model and everything, that's all program basically. That's a program that you will execute, including your model, and that will all be stored in a flash, and then it will run that code and execute in a RAM memory.
Wait, but we got disconnected for a second. Could you back up maybe 10, 15 seconds?
You lost me for a few seconds?
Yes. Yes. Okay. Could you back up 10, 15 seconds?
Of course. So I will try to answer again to your question. So the model and the code and everything that you and the libraries are all going into the programming memory or flash. That's a hard disk of microcontroller basically. So that goes to 1 megabyte of memory, and then when it starts executing actual code and a model, then you use RAM memory, and you will not copy whole code in a RAM memory. You will just use part of the model load in a RAM memory, or you will take the data from the the sensors, and you will load in a RAM memory, process them, run on the model, and spit out the results. So the model and the code and the libraries goes in a 1 megabit flash memory.
Okay.
Hope this answered. Okay. So So usual question is, can we compress the images? You can compress the images and you can use them like that, but the issue is that if you want to use RGB values, you have to decompress the images in a microcontroller, and then you will again end up with the same size of the image, and that's the issue. And also, that's just the image. Where is the model? Where is all the results of the calculation of the neural network? So neural network usually have several layers, and then each layer will output some matrix or array of values, etc. So you have to store all of that in a memory. So you have to make sure that there is some space left after you load your data into RAM memory. Okay. So let's talk quickly about serial port and the speed of serial port, because probably chances are that you will be collecting your data through some ADC, recording data through some ADC, and you will, if you want to create a training set or test set, you will want to transfer that data to your computer. And the common way of transferring the data is through the USB cable or USB port or through the serial. Let's see how fast is that serial. So one of the common baud rates, it can be higher, but one of the common baud rates, I just want to calculate for the common baud rate, is 115,000 bits per second. So let's compare that to accelerometer data. So if you send accelerometer data as a text, which means you will write characters minus 0.07, etc. You have this example. Then for one set of 3 axis accelerometer data, you will take 18 characters. And if you make a back of the envelope calculation and divide the 100,000 bits per second with the 10 bits for 1 byte and with the 18 bytes that we need to transfer one set of accelerometer data, then you will get that we can transfer only 640 measurements per second of the accelerometer. Sorry, somebody is asking something or commenting in the chat. Is the 640 measurement per second maximum sampling frequency we can achieve? Please, if you have questions, please just interrupt me, because I will not always notice the chat. So is the 640 measurement per second maximum? No, it's not. So I just wanted to point it out this because people will not think about the details when setting up serial port, etc. So first of all, you can increase the baud rate of the serial port up to 2 megabits. So 2 million bits instead of 100,000 bits. Secondly, there are other techniques. You don't have to send the data as a text. So these data values are sometimes, for example, if you have data that's number that's, for example, number 200, you can store it in 1 byte, but if you want to print it in a text, you will need 3 bytes. You will need 2, 0, and 0 characters. Okay, so it will be much more efficient if you can send it as actual binary number, byte, instead of printing it in the human readable form text and then send it. So I can explain that in details, but there are techniques with which you can send. So for example, in a Spiker box, Arduino shield, that we are have as a product for long years. We are sending 10,000 samples per second. So that if you really optimize the communication, you can send that much data for sure, even more than that. But you have to know what you are doing. That's why I'm just bringing that up. So that's one of the common pitfalls also, to send the data as a text. And if you add here, for example, people don't think about it. If you add space after comma, for example, then you increase you lower your true output of the data. Okay.
So is the most efficient to use, is it binary data?
Yeah, exactly. As a binary, but that's not human readable. But there is a way instead of print, you use write, and it will automatically send binary. So just different function, and it will automatically work as a binary. So it's not very hard. Just you have to be aware that you need to do that. Okay. Okay, so this is the communication baud rate. Okay, if we talk about EMG, for example, if we have 3000 hertz sampling of EMG and there is 5 bytes per one sample, then actually through this 100,000 bits per second communication, you cannot really send the EMG in real time if you send it as a text. Also, depending on your values, if you have small values, then you will use less number of characters, which means that everything will go faster. And if you have high values, if you measure high values, then everything will go slower. That doesn't make sense. So usually we want to go to binary. Okay. Okay, we can, I don't know how much time we have left. Chris? Yeah, how much time we have left? So
about a half hour.
Sorry?
About a half hour. 30 minutes.
Yeah. Okay. I was thinking of maybe collecting the data with Arduino. Now that we have all the Arduino setup and BLE sense is connected, I want just to show how we can collect some data on Arduino and convert it to edge impulse structure and just upload it to edge impulse.
Yeah, good. Yeah.
Okay. So what we have to do now then, in order to finish that, everything is written here, but first we have to open Arduino Sketch. Here you have the directory in which the Arduino Sketch is stored in the same zip file that I sent you. So data Arduino code. I will do the same thing in parallel. Let me see, stop presenting. Stop presenting. Start sharing.
Good to share.
So if you go into the zip file that I sent you, in the data directory in Arduino code for collection of data, you can find a read accelerometer Arduino sense you can open that. You can close everything that you used before. And there will be a bit more complicated data, but we cover all the parts of this code already. I can cover it if we have time later. But let's just run this code. It will be cool that all of you run this code. So because I want to show you the Python code that converts the data.
Is everybody good? Yeah. Session, did you get it?
Yeah.
No. I know you got it, Fred.
Yeah. Yeah, we kind of rude to ask. Like, really? Are you sure?
I have a.
Stanislav got right.
I have the same error too.
Okay, that's good.
Is it direct?
Okay, I will just unplug and plug back again.
What is the error say?
This is board not sound.
Board.
Thanks.
Try to compile again.
Mine.
There we go.
Okay, mine went through. So this code will wait for you to make quick movement or a movement with a greater acceleration, and then it will start sampling the accelerometer data. It will output that data, fixed amount of data, 1 second. It will output to serial monitor with some special additional string that will mark the beginning of the data. So whenever you do some sudden movement, it will collect 1 second of the data. How I used it? I use it to collect, to use it for a magic wand example. So you can start doing your motion of the magic wand, and it will collect 1 second of that motion. So it will not record anything up until you start moving. Okay. So if you all set that up. Are we all good?
I'm good.
She's loading, yeah.
I think 1 or 2 people are just almost there.
Just went out.
Oh, the mic's not in there. Oh, yes, okay.
Mhm.
So you can try this. Okay, just pick some
What is it?
some magic wand movement, like W or whatever you want, and it will just record 1 second of data whenever you move.
I got mine to work. And I
Okay.
think me as
Okay.
well.
So it's important to make few movements so that you have some data.
Okay. Is it gonna be a problem that at first I didn't realize we needed to make a specific motion? I was just kind of making a random
No, we
motion.
will not train the network now. I just want to show you how you can import this data to the
Understood.
to Edge Impulse. But you have to have some data. Yeah, okay. Then I'm sharing screen, so you can see. Then you just copy data. You select everything, command or Control A and then Control C. You copy data. You go to the editor of your preference. So, and you paste the data, and you see bunch of data, and each example of your movement will start with the data 2 dots. You can save that as what's this? Save it as a test CSV, like comma separated value CSV. So please tell me when you finish that so that we can move further.
You want to open up like something where you edit code? Like you can put it in if you just have Notepad, you can do that. I think.
Yeah, Notepad. I'm using some code editor. I don't know. So if you don't have code editor, then use Notepad or I guess text on Mac. Text edit, whatever is the name of the text edit. The Mac or Notepad on the Windows. And save it as a test.csv.
That's awesome.
Please tell me when you finish so that we can move on.
We're waiting on a couple more people.
No problem, take your time.
Yeah, I just ordered it. I think that's a serial monitor. Right?
Yeah, it is.
Oh.
Just do the port again.
Is there a different VAUD that we should be using? Oh, it's a new file, okay.
Come again, sorry?
Do you want to say it all?
So mine is saving. I'm on a Mac. Mine is saving as test.csv, and then when I do that, it goes to test.csv.rtf.
RTF, so you're using Word something. Can you use a Notepad?
I'm using text edit on
I don't
Mac.
have Chrome 7 anymore. It's only Chrome 7.
She's using text editor on Mac.
Text edit on Mac. Yeah, can you use on Mac text edit?
Yes.
Let me see how to change that. In a text edit on Mac, you can change to simple text format. Text edit on Mac. If you go to format, make rich text.
That's what it's trying.
Okay. Now you have a rich text. Can you please convert? Go to format and then select make plain text.
You don't need to compile it.
Yeah, then you will have the simple version of the text edit, and then you can
After it finishes compiling.
Yeah.
paste that. Go to files,
That's your number. If it doesn't happen after that, computers don't like.
and it should allow you to file save as let's see. Or rename or whatever. It will allow you to save as CSV.
Yeah, I think that's work.
Okay,
Thank you.
no problem. You're welcome.
Where's the serial number? You can try to put don't file that. Now it's connected. Now it's loose. And then serial number. It's because when you were compiling, it was changing the port. Okay, and now yeah, shake it. Harder. Yeah, there you go.
You really got to throw it on.
Yeah, a little bit. So, and then copy that into the text editor and save it. Yeah, just Control A. And tap on it first. And then copy it.
Jessica, if board is not available, try to disconnect from USB from your computer and reconnect again and wait for 10 seconds and try again.
Hello. Thank you.
Okay, are we close to finishing the CSV file? How many people? Can you please just write anything in the chat if you finish this CSV? Just one person? Ah, okay. Okay, okay. 4.
So it's not automatic, it's fully
We will wait few 1 minute more. Because this will be the procedure that you will probably use when you start doing your project. So
is there a way to generate, text file from the Arduino itself. You have to store it somewhere else instead of copy pasting into your monitor.
No. Oh, you can write your software that will do that, but Arduino IDE cannot do that. So
that'll have to be something where wherever you're sending the data, that will handle that portion if you wanted to do that. So
usually how we will use it. So I want to show you this conversion part, but usually you will probably record data with a spike recorder actually at the beginning, and then you will use the spike recorder output file and convert it to the edge impulse format. But later, when you start using Arduino, we will try to figure out if there is something, but Arduino IDE cannot save the output. Maybe if you program something from the CLI, maybe you will be able, but we have to figure that out. So 4 people finished. All right.
When you're done, make sure you put something in the chat.
Oh, perfect. Yes.
I think there might be 1 or 2 more.
Yeah. Okay. Sarah done. Okay. 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 I will continue now. So once you have that CSV, take it, copy it to the different directory that's in data Python code for conversion of data to JSON. So copy it to this directory.
Is this going back?
Shot to the
So let me see where is that. And then when you copy it, the critical part is I now hope that we all have Python 3 installed on our computer. Yesterday we used it and we installed it as one of the steps that Chris was presented. But let's hope that we have it. So on the Mac you have to open terminal. So go to this Spotlight search, enter terminal. On the Windows, go to start menu and type it CMD in a search bar, and then navigate to the directory where you pasted the test CSV. So on the Mac, probably CD and go to the directory. ls to see the files on the Windows CD also, and the dir to see the files. And when you are in the directory,
I have a cheat. I just don't get back to you. Pops up. Another thing we should.
How do you list the contents of something in Windows?
List the contents of?
Yeah.
I think it's
dir. It shows the directory.
Yeah.
then when you are in that directory, call that file, call the convert.py Python file with the Python 3 or just Python, depending on when you type Python in the command prompt, or it will show you what it means that Python means. So in my case, it means that I want to use Python 2 point something. But if I write Python 3, it will offer me Python 3. So depending on the version of the Python, you want to use Python 3. maybe it will work even with Python 2. So paste the terminal code into the chat. So, okay, I will paste it. Just first you have to navigate terminal. I'm answering now to chat. You first have to navigate to the directory and then write Python 3 in my case and convert.py, and that's it. And it doesn't work because I didn't write convert. Then it will ask you file name of the data to convert, and then you type in test.csv. And then it will ask you what's the class label name, and then you say, I don't know, however you want to name the label, but let's say W label or W movement in my case. Don't use spaces, just connect everything. And that's it. Now, if you go to the directory, it's separated all the movements in the separate files, in separate JSON files. So in my case, 43 different movements. I got
So you weren't doing the same stuff that everyone else was doing yesterday?
if you have problems, please ask. Not in the chat. I don't get it. Can you please ask?
Absolutely. I forgot about the mics.
Please, Sarah.
So me and Sachin, we're both using Macs, and when we're attempting to run that Python convert.py function, it's not working, and it's just saying it's invalid.
Yeah, me too.
Okay, can you first type Python? Just Python. And can you see, does it respond with a Python interpreter, and does it say that you have some Python?
No, it just says not defined.
Okay, so you don't have Python in your path. Okay, we will solve that separately. We cannot solve that right here, right now.
Okay.
So you will have to install Python. But it's very strange that Mac.
Someone has Python 3 and they're still experiencing this.
If you type Python 3, does it say something?
Yeah, it says mine says 3 point.
I'm 3.9.5.
Yeah.
No, that's perfect. Then type Python 3 space and then name of the Python file. So the name of the Python file is convert.py. Try with the Python 3 space convert.py.
Invalid syntax.
Yeah, same here.
The same as I did.
You don't have it in the path variable?
That's what I'm thinking, yeah.
Did you guys type on the path?
Maybe they don't have Python as a path variable?
Yeah, probably. But we cannot solve it now for each person.
Okay, we'll figure it out. Yeah, wait,
Command C first.
We don't have much time. We have 5 minutes more.
I'm with you if you want to go on.
Oh.
Okay.
There's at least two of us that have it.
So the code should so the code should generate a bunch of the files, JSON files. So each of these files contains the data for just one movement that you did. You can actually see how this JSON, what's inside. So these are, you just separated all the movements in a separate file and formatted it so that Edge Impulse can recognize it. And then if we go to Edge Impulse and go to some project, let's not go to that project, test 2, okay. So, and you know this is already familiar for you. If you go to data acquisition, there is a button here, upload existing data. You can select, click on choose files, and then navigate to the directory where you did all that conversion. and just select all those files. Let me see. Click Shift. Okay. Open. Automatically split between training or testing. No, we will use, for example, this only for training. In label infer from the file name. No, I will give a label name. Let's say the label is W. That's the movement that I did in the air, and we click upload files, and it uploads 43 files in my case. Everything successfully. Now, if we go to data acquisition, we can see all the movements that we did, that I did. In this case, imported into the Arduinos. So that's the whole point that I wanted to show you, how you can convert an import file. So depending on your project, we will probably modify. Let me stop sharing. Depending on your project, we will probably modify these Arduino file, and maybe even the conversion of Python file. But that's the way how to import in a custom way, so we can make whatever we want. Because Edge Impulse is actually recording just continuous data. You saw yesterday like 10 seconds of data, and if you are not prepared, then if that doesn't fit your experiment, then we will have to make a custom import, and that's the whole point of these two files. Okay, and with this, I will want to thank you all for attending this, and we are finished. Thank you.
Stanislav.
Okay, thank you. Bye.
Bye.
You can quit at 18.
Well.